So now that we've talked about impulse and momentum some, let's take it one step farther and let's talk about conservation of momentum. So just like we had our work and energy, our principle of work and energy, which looked very similar to our principle of momentum and impulse, we had conservation of energy, which was a special situation where if no work was done by non-conservative forces, then energy was conserved. And similarly, we can encounter that here with our impulse and momentum. So if there are no external impulses, or the sum of the external impulses is 0. So either no external impulses, again, external, so not like within the system, but acting outside of the system on the system. If there's no external impulses or impulsive forces, or the sum of the external forces, external impulses is 0, then we can use conservation of momentum. So our conservation of linear momentum, and this is just for linear momentum, just things moving in a straight line, we'll have the sum of our initial masses times our initial velocities equals the sum of our final masses times our final velocities. However many are adding together, however many are in that full system. And typically we use this for particles that are colliding or interacting. So colliding or interacting particles. Typically, like our impulsive forces that we're talking about are things like explosions or things slamming against each other. But our non-impulsive forces are things like weight of the body or something that is so small that it doesn't need to be accounted for, in comparison to like all of the other forces that are acting on it. So typically we can use this conservation of momentum, especially when things are like colliding and sticking to each other, where they're acting as one system. So this is usually where we see conservation of momentum used. And so when we're going to use conservation of momentum, what we're going to do is we're going to set up our inertial frame, figure out what is in the system and what is not in the system. Right, because we may have multiple particles that are interacting or colliding with each other in some way. And so we've got to establish, what are our directions? What are our X, Y, and Z? What is inside the system? What is outside the system? We've got to determine all of those things before we can check if our conservation of momentum can be applied. And if it can, then what we want to do is establish our sense and direction of those initial and final velocities. Right, so we might have this guy moving with a velocity this way, and then he bumps into this guy who starts moving another way. So if we start to establish all of those initial and final velocities, then we can apply either this conservation of momentum or that principle of impulse and momentum, which again was our mass times initial velocity plus the sum of all the impulses. dt gives you the final linear momentum. And so we can use this equation as well in addition to our conservation of momentum. Or we can use other concepts that we've covered, our kinematics, work and energy, F equals ma, all of those things that have led up to this point, we can use those in conjunction with our conservation of momentum, trying to solve some problems. So let's take a look at some examples of how we might use this. So in our first example, we have a 15 megagram boxcar A, which is our little red boxcar on the left there, that is coasting at 1.5 meters per second on the horizontal railroad track when it encounters a 12 megagram, that's our little guy B there, tank car B, who's coasting at 0.75 meters per second towards it as shown. Right, so they're coming in towards each other, and the cars are going to collide. And so when they collide, they're going to stick together and couple. Their little latches are going to lock into each other, and they're going to couple, and they're going to start moving together in one direction. So this is a really good example of where momentum is conserved. Because even though we have two particles, when we bring them together into the same system, there's no external forces. Right? If we treat both cars as being one system. So let's before we get into what we're going to do, let's draw just a little free body diagram of what's happening, which is that these cars come together, they collide and latch into each other. Where when they collide, they each exert a force on the other one. Right? So B exerts a force onto A exerts a force onto B, and they each have their own weights and normal forces acting on each individual car, and when they come together, they have a combined weight and a combined normal force. But all of this is internal to the system, right? There are no external forces. The only forces are from them hitting each other, and those are inside this system if we decide to treat these two particles, these two train cars, as one single system. So this is a really good time to use conservation of momentum. And what we're trying to find is the speed of both cars just after coupling. Right? So we have speed of A initial, speed of B initial. They're going to come together, collide, and then have a speed in one direction. So now that I've kind of established what the system is, what kind of forces we're looking at in here, and whether conservation of momentum would be okay, I'm gonna go ahead and make an assumption, and I'm gonna just guess, because I'm not sure what it'll actually end up being, but I'm just gonna say that to the right is positive. Right, like my normal positive X convention. I'm going to assume that they're going to collide together and move to the right. And now it's probably a good assumption because our boxcar A is moving a lot faster than boxcar B, so it's likely that they'll start moving to the right. But what I want to do is I just want to establish that frame of velocity so I can have my positive and negative signs for this entire system when we go to plug these into our conservation of momentum. So for this first part here, part A, the speed of both cars just after coupling. We're going to use our conservation of momentum, and that says that our sum of our initial mass times velocity is the sum of our final masses times final velocity. So my initial is going to be right before they hit each other, right? And these cars are just coasting, so they have constant velocities anyways. They're not accelerating or anything. And I'm going to add each one together. So first we have our mass of A times the initial velocity of A plus our mass of B plus the initial velocity of B. And then when they come together, they will have the same speed as each other now that they're coupled as like one unit. So that's going to be, the final mass will be both of those. Let me write this a little lower. Final mass is going to be both of those put together. Mass of A plus mass of B times their joint final velocity, since they are moving as one single unit now. So I'm going to start plugging stuff in here. They gave me my initial mass, 15, And you could convert these out of megagrams if you want to. I'm not going to, just because all of my mass units are going to be in megagrams, so I'm just going to leave them all as megagrams. All of those units will cancel out. I have 15 megagrams times 1.5 meters per second. That's the speed at which A is moving. Then I add on my mass of B, which is 12 megagrams, times the speed at it's moving, and make sure we note that this is negative, right? It is moving in the opposite direction from our positive convention that we made, so this is a negative 0.75 meters per second. And this is going to equal my MA plus MB, so that's 15 plus 12 times that final velocity. And this was really helpful, saved us a lot of steps to use this conservation of momentum, because the only unknown in this equation is that final velocity. So if I go ahead and punch all of that into my calculator, I'm going to get a final velocity for both of those together as 0.5 meters per second. The speed after they crash into each other, and I got a positive answer, which means we were correct. It is moving to the right. If we had gotten a negative answer, it just would have meant that we were moving to the left instead. So that's our conservation of momentum. And then our next part here says find the average force between the cars if the coupling takes place in 0.08 seconds. Sorry, not 0.08, 0.8. Takes place in 0.8 seconds. So here, we're not going to be able to use our conservation of momentum, but we can use that principle of impulse and momentum, because we're trying to find a force, and they gave us the amount of time that it occurs in. So if we use that impulse and momentum, principle of impulse and momentum, for just one of the cars. So I'm trying to find this force F. This is the impulsive force that they're talking about. This force that happens when those things, when those train cars hit each other. This is the force we're looking at. For this case, we want to just look at one of the train cars, because otherwise, if we look at this as a system together, the F's just cancel out, right? So let's just go ahead and break out one of those train cars. And I'm just going to do the little tanker guy. And his free body diagram is going to be his weight, his normal force, and then of course the impulsive force F from A, from that boxcar A, that's acting when they collide together. It's acting as that impulsive force there on the boxcar, or on the little tanker car B. So with this guy, now I'm going to use this to analyze those impulsive forces, to use my principle of impulse and momentum to find out what that impulsive force is. So again, that principle of impulse and momentum is going to be my initial mass. I'll just call it MB for the mass of the little tanker car. My initial velocity of that little tanker car plus the summation of any forces dt, any forces that are impulsive with respect to time, is going to equal our final mass times our final velocity. Remember, we're just analyzing this for the single car system now. We're not looking at the two-car system anymore. We're just looking at car B. So in just looking at car B, I start plugging values in, I get 12, and now I'm going to go ahead and convert to kilograms. So 12,000, or 12 megagrams is going to be 12,000 kilograms, right? A mega is 10 to the 6th. A kilogram, 10 to the 3rd for grams. So this is 12,000 kilograms times my initial velocity of v1. And we know that that was a negative 0.75 meters per second. That was given to us back at the very beginning of this problem here. Plus our impulsive force, F. We'll notice F is in the positive x direction, so that's a positive F. dt. We're finding an average force, so we're just going to assume that this force is constant over that instant of the 0.8 seconds that this collision is occurring. So that's my force times the 0.8 seconds in which the collision occurs equals my final mass, which the boxcar itself didn't change. Not boxcar. I keep saying boxcar, but we're looking at the tanker car. We're looking at our car B here. So car B doesn't change. Even though it's hooked to the other car now, again, we're still just looking at the one car free body diagram for this application of our impulse and momentum. And then we found our final velocity was 0.5 meters per second. We just found that in part A. So with all of that, we have all of our ingredients. We can plug this into the calculator to find what F is. So I can find that force, which the calculator gives me 18,750 newtons. So that is the impulsive force that it experiences in those 0.8 seconds when those two cars are coupling together. And I didn't have to use my tanker car B. We could have done this exact same process and used car A. And the only difference is that, you know, our force would be pointing in a different direction. We would have different weights, but it would work out the same. You would get the same answer even if you used car A instead of car B. The trick was that you had to pick just one of them to apply this to get this to work out. Let's take a look at another example where we've got something kind of similar and kind of different at the same time for this application of conservation of momentum. So here we've got two bumper cars A and B, that each have a mass of 150 kilograms and are coasting with the velocity shown before they freely collide head-on. No energy is lost during collision. Determine their velocities after collision. So since this doesn't explicitly say that these bumper cars are becoming like tangled up in each other or sticking together with a wad of gum between them, we're going to go ahead and assume in this one that our bumper cars are going to hit each other and then they're going to come apart. Right? So we're going to say they're not sticking together, they're not staying together, they're each going to have their own velocities after they bump into each other. So when we kind of look at this as a free body diagram in this moment of collision, what we're going to have is car A bumping into our car B, where again we do have those internal to this system. If we treat both of these as one system, there are forces between them, but there's nothing else happening. Like there's no other kid is coming up and shoving one of the bumper cars to get them to bump into each other. You know, there's no external forces acting on this. It is just the forces from these two interacting with each other. And so what we're going to do is we're going to try to find out what those final velocities are after the collision there. So this is another one. It's a great case of conservation of momentum. where we're going to assume all of those impulsive forces, everything's internal, there are no external impulsive forces. And then I'm going to make my positive convention for my velocities. I'm going to say, again, just for simplicity, let's just say to the right is positive. So our velocities, any of them to the right are positive, to the left are negative. And we'll apply our conservation of momentum. So again, that's our initial velocities. Sum of our initial velocities times initial masses equals sum of final velocities times final masses. Where we have now, instead of a collision where we're sticking together, they're each going to have their own mass, MAVA initial plus MBVB initial equals MAVA final plus MBVB final. Right, so now I've got two different velocities to contend with instead of just one, since they're not stuck together, which means I have two unknowns in this equation, right? My masses are known, so I know all of my masses. My initial velocities are known, but I don't know VA2 or VB2. So I'm going to need to come up with a second equation to kind of figure out how to relate these velocities together. And so if I go back and look at this prompt that they gave me, bumper cars are coasting velocities, they freely collide head on. If no energy is lost, during collision, determine their velocities after collision. That if no energies is lost is a really good key indicator that our energy is going to be conserved as well. Right, so we've got conservation of energy going for us in this problem too. So we're going to go ahead and use conservation of energy and see if we can get another relationship for our final velocities so that we can solve for those final velocities. So with this, I'm going to use conservation of energy, and again, that's your initial kinetic energy plus your initial potential energy equals your final kinetic energies plus your final potential energies. In this, we've actually got no changes in potential energies. The only energy happening here is kinetic, because there's no movement in our y direction for weight to be contributing to potential energy. There's no springs. So it's all entirely kinetic energy in this conservation of energy equation. 1/2 MAVA1 squared plus 1/2 MBVB1 squared, and then no potential energies. And then we repeat that for the final kinetic energies. So 1/2 mass of A times velocity of A final plus 1/2 mass of B times velocity of B final squared plus 0. So now I've got two equations, two unknowns. I can work through those to solve for my VA and my VB. So I think I'll do... I'm going to start with plugging everything into this longer one, my conservation of energy. See how far I can work that one down, and then I'll start working with my other conservation of momentum equation. You can do these in whatever order you want. I'm just going to try to go about it the best logic that I can, but everybody's brain works differently. You can, muscle this out, math this out however you want once you have your setup, really. So both of those cars weigh 150 kilograms, which actually kind of makes things a lot easier for us, because we'll notice that in both of these equations, there are mass terms. And if all of these masses are 150, and every single one of these has a mass term, we can actually just cancel this 150 out. And all of these have a mass term. They're all the exact same. I'm going to go ahead and cancel all of them out. And so then what I get is 1/2 times my initial VA1, which he's kind of hiding under here, but whoops. We have 3 meters per second. So 3 squared plus 1/2 times, now notice that my VB1, my initial velocity of B, whoops, is 2 meters per second in the negative direction, but it actually doesn't matter for conservation of energy because it gets squared anyways. But it's good to note that it is actually a negative. And that equals, you know, now that I think about it, I could have canceled out all these 1/2s as well, and I might do that too. Simplify my life some. 1/2 VA2 squared plus 1/2 of VB2 squared, and I'm gonna cancel all these halves out. And so what I get over here is gonna be 9 plus 4 equals VA2 squared plus VB2 squared, and 9 plus 4 is just 13. So I've kind of worked this down as about as far as I can, so I'm going to see what I can do with my conservation of momentum equation, plugging things in there. So I get VA1, which was 3, plus VB1, which is -2, equals VA2 plus VB2. And so if I simplify this, and I'm going to go ahead and substitute in, I'll just substitute in my A. So I'll say 1 minus VB2 equals VA2. I'm going to take this term and I'm going to plug them in here. So when I do that, now that I have these two combined, I have 13 equals 1 minus VB2, that entire term squared, plus VB2 squared. So normally I don't work out so much of this algebra, but I think it's important to kind of talk about how we solve some of these problems sometimes, because sometimes I skip some steps and I know that some people get confused sometimes. And that's not your fault. It's just because I'm skipping steps. And so I think we should talk about some ways to solve problems when you get these kind of ugly, not nice things to solve. So, for example, when I get to this point, I know I need to FOIL out this term from math. So I get 13 is 1, and then minus VB2 minus VB2, right, so that's multiplying the first times itself, right, 1 times 1 time by itself, and then you multiply the inners by themselves, and then you multiply the last by itself, plus VB2 squared, plus VB2 squared. And so I'm going to simplify this down and move the 13 to the other side, so I get 0 equals -12 minus 2 VB2 plus 2 VB2 squared. And when I get to this point, you might be like, oh no, you know, oh gosh, do I have to go through and I have to try a bunch of things and try to figure out, like I have to separate out, you know, what the different roots are? And the answer is no. Don't put yourself through more trouble than you have to. I would 1000% of the time use a calculator for this. And what I mean by that is make the calculator solve it for you. There's no reason to have worked so hard to come through your calculus classes and, you know, maybe you're in differential equations or linear algebra and not be able to just use a calculator to your advantage. There's no reason to brute force a bunch of algebra all the time. So I'm going to pull up a calculator, one that most people have. Whoops, okay, that's an ad. There we go. So this is just a TI-84. You can find these. You can find this program online, even if you don't have a TI-84. But if you have some kind of calculator that has graphing capabilities, I would really highly recommend getting one if you don't, because they can save you so much time in that algebra. And what I mean by that is you can just plug in equations into your calculator and have them find those roots, have them find those zeros for you, have them find those maxes and mins for you, have them find whatever value you want. It can save you a lot of time. So if you hit this y equals button, you can type in your equation. And so for us, our equation was -12 minus 2vb, which I'm going to replace with x's as we're writing this in. Just so we can write it in the calculator that way. So -12 minus 2x plus 2x squared is what I'm going to type into the calculator here. So -12 minus 2x plus 2x squared. And then I'm going to hit the graph button. And so you can see when I graph it, it shows me where those zeros are. And even if I wasn't sure, they have these, if I hit second and then I hit calc here, right, this blue word calc. So second makes it the blue word. I can find the zeros, right? I can find the values, max, min, whatever I want. I'm going to hit 2 because I want a 0. And the way you find those is you go to the left of where you think the 0 is, and then you go to the right of where you think the 0 is, and then you hit enter, and it gives you those zeros. So for this one, see, I can use my arrows, I can move my little dot around. So this is left of this 0, enter. Then I'm going to go to the right of the 0, enter, and then I'm just going to hit enter again, and it tells me that my 0 is at x equals -2. So I have one 0 at x equals -2. So I'm going to put that over here, -2, and again that x is really VB2. So VB2 could be either -2, or it could be, I do second calc, find my zeros again, come all the way around, left side, enter, right side of the 0, enter, enter again, that is x equals 3. So for me personally, this is how I solve so many systems of equations, and honestly, we didn't even have to take it this far in combining them. We could have probably written out this equation and this equation with multivariables. Inside of, where did it go? Here it is. Inside of our y's here, with multivariable capability, which some calculators can be a little bit weird about. The TI-84 is kind of touchy on it sometimes. But I could have entered in down one line, entered in another equation, and then found where those equations intersected to find these values. So this is often why I blow past the algebra, because there's so many good, quick ways to solve it in your calculator and not force yourself through it. That if you learn some of those tips and tricks, you can save yourself a lot of time. But I know it takes a lot of time to learn these tips and tricks and to get good at them. So never feel bad for having to write out all your algebra steps or make it a little harder than you think it should be. It's perfectly okay. All of this takes practice. Which brings us back to where we were, which is that our VB2 we had two possible answers for. It could be -2, or it could be +3. But we'll notice if we go back to our original problem up here, VB was initially traveling at -2 meters per second. So it's not just going to continue traveling at -2 meters per second, right? That was our initial speed. That's the first route that we found was our initial speed. Because it's not like VA and VB are phasing through each other and just moving straight ahead. Instead, what this tells us is that this was our initial, VB, and this is actually our final VB. VB2 is 3 meters per second. And if I plug that into this guy over here, I'm going to get that my VA2 is negative 2 meters per second. So they essentially swap speeds, right? A was moving at positive 3, B was moving at negative 2, and they switch where A is now moving at negative 2, and B is moving at positive 3. So I hope those calculator tips were more helpful than just a waste of time, but it's just a good way to say there's a lot of different ways to solve these problems. There's a lot of tools at your disposal. You don't have to, go through all this hard math work because you've done so much of that already in all of your classes. Here, it's really about understanding how you set up the problems, setting up those problems correctly, rather than just forcing through algebra. So I've got just one more example that we'll work through today, so let's go ahead and take a look at that one. Alright, so we've got one last problem for you, and it's a little different from our first two in that instead of having two particles come together, we're actually going to have them start together and come apart. So in this case, we have an 80 kilogram man that can throw a 20 kilogram box horizontally at 4 meters per second when he's standing on the ground. But if instead he firmly stands in the 120 kilogram boat and throws the box, determine how far the boat will move in 3 seconds. So there's a lot going on here. There's a lot to process in this question. And I think the first thing we want to do is look at what's happening, right? What are the actual dynamics, physics, the actual thing that's happening in the real world in this situation? So initially, we have our man, our box, and our boat. All of these things are together, right? They're all standing together. They're in our little picture on the left. They're all standing together. And then the man throws the box, right? And so this, again, all is one system together. We have our man throwing the box. So he's imparting a force on the box, and the box initially was just sitting there in his hands. So it's kind of imparting a force back on the hands when the hands are pushing it. The force, or the box, was initially not moving, so it's stationary, its desire to stay stationary causes a force in return. So we've got our man and our box, and they are, when that box is thrown, they're imparting forces on each other. Now, of course, this is still internal to the system, right? The system being man, boat, box, right? That's all internal to this system, those forces acting on each other. And then what happens after the box is thrown is that right after, they're not touching each other anymore, right? Right after that box leaves the man's hands. Here we have man. Here we have box, where now box is moving to the left, right? It's got some velocity moving to the left, no longer touching boat and man. But because they're sitting in the water and not on solid ground, and you may have seen examples of this in real life before when you're pushing off a dock or when you're in a boat and you're trying to grab on and you just can't get any traction, the boat and the man are going to move in the opposite direction, right? So because of that force of them coming apart, right, that man throwing the box, it moves the box forward and it moves the man back. Man and the boat go in the opposite direction. I'm going to call this velocity of box. I'm going to call this velocity of man boat, MB. VMB for man boat. Because they stay together. The man's not going anywhere. He's standing firmly inside of the boat. So they're going to move back together as one. The box is going to move in the other direction. So again, this is another good case for our conservation of momentum because there are no external forces, right? All we have are those, or there's no external impulses, I should say. Our momentum is going to be conserved. So the box takes some velocity and the man in the boat takes some of the velocity. So if we go ahead and start our setup, we're going to have our sum of our initial mass times initial velocity is going to be the sum of our final masses and velocities. So our initial mass and velocity is just the man standing there with the box. Nobody's moving. We're just sitting there in the water. Nothing's happening. No initial velocities whatsoever. So 0. And then we're going to look at our final velocity. So we know we have that velocity of the box. So we're going to have the mass of the box times the velocity of the box plus our man and our boat who are moving. So our man and our boat are 1 unit still. So mass of man plus the mass of the boat times the velocity of the man-boat combo as they float away in the opposite direction. I'm going to start plugging some things in here and see how far we can get with this. Because we're given all of these initial masses. Our mass of our box is 20 kilograms times the velocity of the box, which we don't know. And I'm going to say that, I made my mistake and I didn't say which direction was positive. I'm going to say my velocity is positive to the right, which means actually this should be a negative 20 times velocity of the box, because that velocity of the box is in the negative direction. So negative 20 times the velocity of the box plus mass of my man is 80 kilograms plus mass of the boat is 120 kilograms times the velocity of the man-box combo. So I've got 2 velocities that I don't know. I don't know velocity of the box, and I don't know velocity of the man in the boat afterwards. And I know you may be thinking, well, what do you mean I don't know those? I'm told that he can throw the box horizontally at 4 meters per second. But that's when he's standing on the ground. When he's standing on the ground. That's a very, very important caveat to this, because it is not the box that's moving at 4 meters per second. That's the velocity of the box relative to the man, right? But now both the box and the man are moving. So because both the box and the man are moving now, it is not just 4 meters per second. That 4 meters per second is relative between the box and the man. And it's been a while since we've seen this relationship, but we're going to have to use our kinematic relationship where we have relative velocity. Velocity of our box is going to be velocity of the man and boat, plus the velocity of the box with respect to the man. Right? So we know this term. This is the term that was given to us. He can throw the box at 4 meters per second when he's standing on the ground. So this term, this is our 4 meters per second term. And now we can use this, it gives us a second equation to solve between these two to find what our velocity of our box is and what our velocity of our man boat is. So our velocity of our box is going to be our velocity of our man boat, and then this is going to be minus 4 meters per second, because again he threw that relative velocity of v box with respect to man is still in the negative direction. That's going to be a negative 4. And we can go ahead and plug that in, or we can simplify this relationship here. I might do that. Here I get 20 v box equals 200 v man boat. So velocity of my box is 10 times the velocity of the man in the boat. And if I pop that in here, 10 times velocity of man and boat equals velocity of man and boat minus 4. And that is going to give me my velocity of man and boat is 0.364 meters per second. And I got a positive, so that's to the right. And if I substitute that back in, I know that my box is 10 times greater. So velocity of my box is negative 3.64 meters per second, or 3.64 meters per second to the left. And I boxed those, but I didn't actually answer the question at all. Right? I didn't need to find velocities. It wasn't what my question asked for. I needed to find velocities so I could find out how far the boat was going to move. So I'm going to assume that my my velocity is constant in my x direction. Which makes sense, because this is really, after the box leaves his hands, it's really just a projectile motion problem. Your velocity is going to be the same in the x direction. So my, the distance oh, not my box, my boat, sorry. I want the distance my boat moves, not my box. But again, we'll still assume constant velocity for this boat floating away. How far, what's that distance s that it moves? Assuming constant velocity, I'm going to get that my boat moves the velocity, velocity times time. So my boat velocity was 3.64 meters per second times 3 seconds. And that's going to give me that the boat moved 1.09 meters away in 3 seconds after throwing that box. So just remember, we can always use those old kinematic relationships, work, energy, F equals ma, all of that stuff that we've talked about before can still come back. You can still use those in these problems. But you now have this new tool of conservation of momentum in your tool belt, in this big hodgepodge of equations we can use to solve problems.